Hello guys, how are you today? So today I'll be explaining the chapter 2 physics course questions. And let's start with section 2.1, rubbing together some materials. Can a plastic rod be charged if rubbed against another plastic rod? Definitely not, because if you rub two objects made of the same material together, it's gonna cause friction and heat. And to make it charged, okay, they must be rubbed against a different material for it to be charged. So here we will say no, must be rubbed against a different material. Now we move on to section 2.2, electric charges and charged bodies. Consider four charged objects, A, B, C, and D, such that A repels B. Okay, so let us circle. We have A repels B, meaning they are the same charge, and it attracts C, meaning they are opposite charges. C repels D, meaning they are the same charge. If D is positively charged, that means C is positively charged. If C is positively charged, that means A is negatively charged. And if A is negatively charged, that means B is negatively charged. So definitely the charge on B is negatively charged. Moving on to question number 3, how many electric states exist? We have two electric states, which are the positive and the negative states. Determine how the charges would interact in the diagram below. Diagram 1, diagram A, diagram B, diagram C, and that is it. So since these two have the same charge, they are gonna repel. Since these two have opposite charges, they are gonna attract. So repulsion is like this, attraction is like this. And since these two have the same charge, they are also gonna repel. Now we move on to section 2.3, question number 5. Give some examples of conductors and insulators. Any conductors could work, such as metals, electrolytes, whatever. And insulators could be like plastic, air, and etc. So we should state them. Now G, differentiate between conductors and insulators. What we need to know is that conductors will allow the charge to move throughout the object. So let me draw two objects. Object 1, object 2. Okay? Each of them have electrons. Let's say these are the free electrons. But this one has free electrons, whereas this one has fixed electrons. So I'm gonna write free and fixed. In the one that has free electrons, we call it a conductor. Why is that? Because if you bring a charge to it, it will come here, and then this will bring it here, and it will move, and it will distribute the charge to all the electrons, which will distribute it evenly all throughout the object. So it becomes charged. Whereas in a fixed object, or not a fixed object, in an insulator that has fixed electrons, if you bring a charge to this electron, it's not gonna move, so it's not gonna be able to give it to this one. So that's why we say in the conductor, the flow of electric charges is allowed to pass, whereas insulators do not allow them to pass. Now we move on to section 2.4, sharing an electric charge. A metal rod placed on a beaker is in contact with a light metal-coated ball. You touch the end of the metal rod with a charged glass rod, and the ball at the other end is repelled. After the charged rod is removed, the metal rod still repels the ball. Suppose that now you touch the ball with a metal rod that you hold in your hand. What do you predict will happen and why? So what's gonna happen? Let me explain in detail first what happened. So we had these two metal balls. They were touching each other. Okay? I think I will draw it like this. And they are neutral. Okay, because they didn't tell us that there was any sign of charging. So we're gonna assume it's neutral. So let's say 2 positive, 2 negative. Now, if you bring a charged rod, let us say for example, a negatively charged rod, what's gonna happen is that this ball needs to become positively charged to become attracted to this rod. So either way, because it is neutral, it needs to become attracted to this rod. Anyways, it will be attracted to this rod. So for it to become positively charged, what it's gonna do is that it's gonna give its electrons to this ball over here. Okay, so what's gonna happen is not that now you have the negatively charged rod. Okay, you have the ball, but because it gave its electrons to the other ball, okay, it becomes positively charged. So now there is a force of attraction between the negatively charged rod and the positively charged sphere. And what leaves us here is we have 2 positives and 4 negative charges, which means it is technically negatively charged. Now, because it is negatively charged, there is gonna be a repulsion. Okay, so what happens is we're gonna bring our hand. Let's say our hand is blue color, and okay, I can't draw a hand, but let's say this is our hand, our deformed hand. Okay, and then we are touching the sphere. Because it is negatively charged, okay, we're gonna do something called grounding, because our body is a better conductor than the metal sphere. So what's gonna happen is the negative charge is gonna flow into our hand. So what's gonna happen is we're gonna feel an electric shock, but then the ball will lose its charge to our body. Now, of course, if you're wearing shoes, you know, shoes are made out of rubber, plastic, whatever some shoes are. It's gonna prevent it from reaching the earth. But if you touch it and you are barefoot, it will reach the earth. Okay, so that is pretty much it for question number 7. Question number 8, we need to define earthing. Earthing means to remove the charge of an object by making it in contact with a bigger conductor. So for example, in the case of the one above, it was negatively charged. We put our hand and we are a bigger conductor. And then the charges, which is the negative charges, because remember the positive charges can never move, they are stuck inside of the nucleus. But then the negative charges, which is the electrons, is gonna flow from the sphere into our hands. Now we move on to question number 9. Describe the process of charging by induction and earthing. Now, induction and earthing, it is 5 steps we need to remember. So 1, 2, 3, 4, and 5. Okay, so I'm gonna say them orally. Starting with number 1, you put an uncharged metal sphere on an insulating stand. After that, for number 2, a positively charged glass rod is brought near the sphere without actually touching it. Okay, for number 3, without removing the glass rod, the sphere is earthed or grounded. For number 4, the glass rod is moved far away, and number 5, the sphere is left with a negative charge. So let us draw what exactly is happening. We're gonna have a sphere. In the sphere, we're gonna have like 3 positive, 3 negative. It's neutral. Then what we are gonna do is we are gonna get a charged rod, which is positively charged, and what's gonna happen is that it's gonna attract the negative charges. Now what's gonna happen is we are gonna earth this ball, and to balance out the positively charged, the positive charges, we're gonna bring the negative charges from the earth, or in other terms, the negative charges from the earth are gonna come, they are gonna go, and they are gonna balance out, okay, because this already is attracted to the positive. Then the electrons from the earth are gonna come and to balance this out. Then we are gonna stop grounding it, and we are gonna remove the positively charged sphere, and we're gonna be left with a negatively charged sphere, which is 1, 2, 3, 4, 5, 6 negative electrons. So this is what it happens. Now we move on to section 2.5, attraction of neutral bodies by charged objects. Suppose you hold a metal rod in your hand and you move one end of the rod toward a positively charged sphere, suspending from an insulating thread. What do you expect to observe? So remember, anytime you have a neutral ball and a charged rod, it will always be attracted to it. So what we expect to happen is that the metal rod will be attracted by the sphere, or the opposite, the sphere will be attracted by the metal rod. Now, how do you explain this? Because it's neutral, it has the same positive and negative charges, then something called polarization is gonna happen. Polarization states that, okay, this is an atom. It has one side being positively charged, one side being negatively charged. So, if it is neutral, and we bring towards it a positively charged sphere, for example, so you bring to it a positively charged sphere, what's gonna happen is the negative side, so let's say it was originally like this, the positive is on this side, what's gonna happen is that the negative side is gonna flip so that it meets the positive side, and we call this polarization. Or in other terms, by induction, a negative charge will appear at the end of the rod closer to the ball. Induction meaning because of this, the polarization happens, so it is technically induced. Question number 11, you have two metal spheres of the same size mounted on insulating stands, a strip of plastic and a piece of paper. Describe what you could do to give the two spheres equal charges of the same sign. You rub them on the same now, to give them the same charge, what we're going to happen is we're going to take the plastic strip and we're going to rub it on the paper. Now remember, plastic or polythene is negatively charged, so it's negatively charged. And then the paper becomes positively charged. We touch one of the spheres with the paper, okay? And then by touching, this is by conduction, the sphere becomes positively charged because the positive charge will flow from the paper to the sphere. Then we touch the charged sphere, the positively charged sphere, to the second sphere, and then by conduction, it's also gonna become positively charged. Now, equal charges of opposite signs, you're gonna rub the plastic strip with paper. Okay, now the plastic is negatively charged, the paper is positively charged. You're gonna touch one of the metal balls with the plastic strip, so by conduction it becomes negatively charged, and you're gonna touch the other one with paper and it's gonna become positively charged by conduction. But if they don't want equal charges, however, if they want equal charges, you are gonna put the two balls next to each other and they have to be touching each other. Then you are gonna get the negatively charged plastic strip. You are gonna touch one of the balls, okay, and then there will be a slight moment in which this ball becomes negative by conduction, and then the other ball will become positive because of polarization. And that is how you get equal charges of opposite signs. Now we move on to question number 12. Two metal rods are mounted on insulating blocks and aligned along a common axis with a space between them. One is positively charged and the other is negatively charged. A light sphere with a conducting coating suspended by a long insulating thread is introduced into the space between the rods. What do you predict will happen, and what reasoning do you base your prediction? Now, look, they told us one is positively charged, the other is negatively charged. And because they are like the same two metal rods, then they probably have the same magnitude. So what's gonna happen is that there is an attraction because one is positively charged and one is negatively charged, and since they have the same magnitude, they are gonna attract each other. Now, question number 13, two identically charged spheres are placed at a distance of 1 centimeter. This is the distance. We need to change it to meters. So then it is going to be 0.01 meters from each other. The magnitude of the electric force between the two spheres is 5 newtons. So this is the force. We know that the equation is force is equal to the constant K. We need to memorize the value of this constant K. Okay, multiplied by quantity 1 multiplied by quantity 2, then divided by the distance squared. Now the value of K, you have to memorize it. It is 9 times 10 to the power of 9. Okay, so if we substitute what we have, one thing also I forgot to mention is that two identically charged spheres means Q1 is equal to Q2. So in this case, it's like you're saying Q2 multiplied by Q2, which that means it is Q squared if you're gonna forget about the 2. So it is Q squared. So Q squared divided by the distance, which we got it to be 0.01 squared, times k, which is 9 times 10 to the power of 9, is equal to the force, which is 5 newtons. Moving it to the other side, you are going to get q squared is equal to 5 multiplied by 0.01 to the power of 2 divided by 9 times 10 to the power of 9. Now, of course, to get rid of the square, it's going to become a radical. So that means q is equal to radical 5 times 0.01 squared divided by 9 times 10 to the power of 9. Now, if you do it on your calculator, radical 5 times 0.01 squared divided by 9 times 10 to the power of 9, you are going to get approximately 2.357, which is 2.4 times 10 to the power of negative 7. So that is it for question number 13. Now we move on to question number 14. Describe how bringing a neutral conductor close to a charged object causes attraction between the two. Now, what you need to know in a neutral object, a neutral conductor, okay, if you bring, let's say, a negatively charged rod, what's going to happen is that the positive charges, okay, within the conducting sphere are going to be attracted towards the negatively charged plastic rod, which in this case makes it a positively charged conducting sphere, okay? Now we move on to section 2.6. How many electrons should a neutral object gain or lose in order to acquire a charge of this? What we need to know is that the charge Q is equal to plus or minus the number of electrons multiplied by the elementary charge. We should memorize that the elementary charge is 1.6 times 10 to the power of negative 19. Okay? Q is given to us, which is 7.4 times 10 to the power of minus 9, divided by 1.6 times 10 to the power of minus 19, and if you do it on your calculator, you are gonna get 4.625 times 10 to the power of 10 electrons. In a typical lightning bolt, an estimated charge of 20 coulombs is transferred from a cloud to Earth. How many electrons make up the lightning bolt? We have Q is equal to N times E plus or minus N. We have Q is 20, it's equal to plus or minus N times elementary charge, which is 1.6 times 10 to the negative 19. We're going to divide, so it becomes 20 divided by 1.6 times 10 to the negative 19. And we are going to get 1.25 times 10 to the power of 20. This is 0 electrons. Now, how is an object positively or negatively charged? It is based on electrons, so if it gains electrons, it's negatively charged. If it loses electrons, it's positively charged. Now we move on to section 2.7, charge detection. An old-fashioned gold leaf electroscope consists of two thin gold leaves suspending from a metal rod in a glass container. You electrify a plastic rod, then bring it near the rod. That means this is negative. Okay, you bring it near the knob of the electroscope and the gold leaves separate. What happens is that because it is repelled, okay, the electrons are going to go all the way to the bottom to the gold leaves, causing them to become negatively charged. So this is gold leaf 1, gold leaf 2, minus and minus, they are going to repel. So they are going to end up being further like this. Now, when you remove the rod, the electrons are going to go back to normal. It's going to continue becoming a neutral object. So then the leaves are going to fall straight once again because it is neutral. So that's pretty much it for number 18. Number 19, explain how to distinguish experimentally between positively and negatively charged and electrically neutral bodies. Okay, so how we're gonna do this is we're gonna use the experiment that is in number 18, the gold leaf thing. So I'm just gonna draw a diagram. We have the golden leaves over here. Originally they are neutral, so they are falling down. Okay, so what we're gonna do is we're gonna bring an object. We don't know if this is positive, negative, or neutral. If it is neutral, okay, and let's say we have negative charges here, positive, negative, etc. So it's neutral. You bring next to it a neutral, nothing is gonna happen. So if nothing happens, that means it is a neutral object. But however, you bring an object that has a charge you want to figure out. Okay, you don't know what is the charge of this object. Is it positive? Is it negative? Because if it is positively charged, it's gonna make the leaves diverge. And if it's negatively charged, it's gonna also make the leaves diverge. So what we are gonna do is we are gonna charge this dome into something we know. So for example, let's say we gave it already electrons. So it's negative, then minus, plus, okay, etc. And now, since the dome is negative, and let's say you brought this charge over here. So if you bring this charge over here and it turns out to be negative, now I forgot to mention one more thing, is that if you charge the dome negatively on the top, it becomes positive from the bottom. So the leaves are gonna diverge. Okay, so since the leaves diverged originally, it's gonna stay like that for a while. Now, if it is negatively charged, what's gonna happen is that the negative charges are gonna come down again, okay? And then the leaves are gonna go back to how they were originally, because at some point it becomes neutral, same positive, same negative. But then, because of the excessive amount of electrons falling down, okay, it's gonna end up being negatively charged here and negatively charged here, so it is gonna return to repelling like this. Okay, now if it was positively charged, what's gonna happen is that the leaves are already diverged. If it's positively charged, then more electrons are gonna go up and the leaves are gonna diverge more. So that's pretty much it for question number 18. Sorry, not 18, number 19. Yeah, no, we don't have a lot. Now, moving on to 2.8, number 20. What makes a person's hair stand when he or she touches the dome of a Van de Graaff generator? Definitely, there are some charges at the top of the Van de Graaff dome. So when you touch it, your hair is gonna accumulate, it's gonna take in the static electricity, and then your hair starts to stand or fly. How does charging the spray gun help spray the paint evenly and help save paint? If the solvent in the paint is a petroleum product, what hazard might result from excessive charging of the gun? Now, paint drops are usually negative charge, okay, and they leave the gun and they are attracted to the wall because the wall is grounded, meaning probably if these are negatively charged, then the wall is positively charged. So what's gonna happen is that they become attracted to the wall and they place a thin coating. Now, in petroleum, there is some static electricity. It might ignite the petroleum, might cause it to cause a fire, basically. Now, how does the lightning conductor help protect buildings? What's gonna happen is that the conductor, when lightning hits, especially the tall buildings, like on Burj Khalifa, if you look at the top, there is a lightning conductor, like a small antenna, then the lightning will hit it because Burj Khalifa is the tallest building. It definitely hits the taller buildings first. So what's gonna happen is the lightning will go through the conductor, okay, and it will provide like a path for the electrons to flow without damaging the buildings. Now, how can static electricity help in seeing fingerprints? What's gonna happen is the thing they want to investigate for fingerprints, they put it on a plate, they connect it to a negative terminal of a power supply. They place powder on the metal plate, it's connected to the positive terminal, and there's gonna become some electricity, okay, some electric changes, some electric attraction between the negative terminal and positive terminal. And what's going to happen is that the powder particles will lose their positive charge and will acquire a negative charge, okay? And so then they stick only to the ridges of the fingerprint, and that helps us see the fingerprint. Now, how does the electrostatic precipitator work? Usually what's going to happen is that we have two uncharged metal rods, so we're going to say not for not charged, and they are metal, both of them. Then we have a grid in between, and this is positively charged. And then we have some positively charged ions. So what's gonna happen is that the smoke is gonna come, and probably, let's say the smoke is charged, let's say it's positively charged. What's gonna happen is that it will come over here, here, possibly here, or here. And because you have a positive charge over here, okay, and these are already positively charged, it's gonna come to this metal plate, which is neutral. Already, since it is neutral, it's gonna attract the positive charges, okay? And if we have another positive charge that will push it towards this neutral, it's just helping it even more to come and stick here. So how they wrote it was a fine wire grid inside the precipitator is kept highly charged, so that a discharge will always occur between the fine grid and the two concave metal plates, which are earth. When the smoke and dust particles carrying waste gases rise through the region between the grid and the concave metal plates, the charged dust particles, so they are charged, most probably positively charged, are repelled from the wire grid and attracted to the earth plates where they are deposited. So that's it for E. Now for question number 21. On Jack's birthday, he has fun rubbing balloons on his jumper, then putting them against the wall. The balloon sticks to the wall. If the balloons were given a negative charge, what type of charge did the jumper get? Definitely rubbing two objects, one will acquire, for example, positive, the other will acquire the opposite charge, which is negative charge. So if the balloon got the negative charge, then Jack's jumper got the positive charge. Jack tried rubbing two balloons on his jumper and making them stick together. Would they? Definitely they would not, because if Jack's jumper got the positive charge, then the two balloons get the negative charge. Then definitely they are going to repel each other because they have the same charge. Now we reached the last section we have, which is section 2.9, the electric field. So in the expression F, which is the electric field, is equal to the quantity of charge multiplied by the energy, is the charge Q0 the one creating the electric field or the one feeling the electric field? It's definitely the one feeling the electric field. The one creating the electric field is not affected by the field itself. So let's say you have this charge over here, and then it's a positive charge, so the arrows are going to be pointing away from it. Okay, now this positive charge is not going to be attracted to itself because it is the one that is releasing or creating this electric field. So definitely this Q over here is the one that will feel. So any charge over here, for example, negative, it's going to feel this electric field. So we are going to consider this negative charge and not the positive charge. Now define a uniform electric field. A uniform electric field means that parallel lines of the electric field is moving. So let's say we have positive, negative. What's gonna happen is that these parallel lines of the electric field are gonna move like this. So they're moving all at the same magnitude and direction at any point in space. So if you come here, for example, you come here, or here, or here, or here, or here, or here, or here, they are all gonna be experiencing the same magnitude and then the same direction. Okay, now 24 grid. Describe electric field around a point charge. An electric field is definitely a vector quantity. That means it has both magnitude and direction. The magnitude of the electric field is the force, so electric field denoted by E. So my apologies, F is the force. This is the one feeling the quantity of charge feeling the electric field, and E is the electric field. So to describe the electric field around a point charge, it's very simply the electric field is equal to the force divided by the electric charge. Okay, now we move on to question number 25. Draw the electric field patterns around two positively charged particles placed near each other. So what you need to do is just draw positive, positive, then draw that they repel each other. So it needs to be moving like this. The arrow for the positive is pointing away from the sphere. So this, my bad, is like this. And there we go. Now one thing we also need to know is that the closer something is to the source of the electric field, the stronger the electric field is. And if something is in the center of the repulsion, there is no force acting on it. So definitely that's it for section 2.9. Thank you guys for watching, and I hope you do well tomorrow.